Okay, so here's my setup. I've already plugged everything in, and what I have is I'm using a quad op amp, and the reason for that is because we're going to be using additional op amps a little bit later in this video for the next stage of control. I'm only using two of the op amps right now for this circuit, one for the current, one for the voltage. And the other two op amps are right now just acting as basically impedance converters, because I'm using a couple of potentiometers here to drive the set points for the current and the voltage, and I don't want the summing junction to be impacted by the fact, because the summing junctions are using just two resistors for the summing. Then because these potentiometers, as I increase it, basically you're going to have the resistor acting in parallel with the V-sense, and it's going to affect the drive into the summing junction. You really want to drive those summers with low impedance sources, and obviously these pots are not low impedance. So the two op amps that I've got configured for just basically impedance conversion, they're just acting as a voltage follower configuration, so it's just got a short between the output and the negative input, and they allow me to drive the set points with a low impedance source, and the output of the main differential op amps, of course, is also low impedance. And the op amp I'm actually using today is going to be the TLE2144 from Texas Instruments. All right, it's got quad op amp. It comes in a 14-pin package. It follows the standard layout for most of these quad op amps. So if you want to substitute for something else, be my guest. You can either put better ones that have, higher gain, higher bandwidth, lower input impedances, lower noise, and things like that. I can't remember the exact specs of this one, but I had a few of them in my goodie bag, so that's why I picked it. No other reason than that. It's able to work between plus and minus 40 volts, I believe. I'd have to check the specs again. Anyway, we're going to be supplying it today with plus and minus 12 volts. So you got the VCC plus and VCC minus. So that's what we're going to use as a 12 volt supply. It makes no difference whether it's 12 volts or 15 volts as far as how the circuit's going to work. I'm using V input 1 as the differential amplifier for the voltage, and I'm using V input 3 as the differential amplifier for the current. So this is what I've got set up on the board, and what we're going to look at to start with is the voltage comparator and have a look at how that operates. All of these resistors I'm using, they're standard 5% low cost resistors. I actually got a box full from Element 14. They come in little strips of 100. All right, they come in these little packets. They come in 100. They're very, very low cost, and you can actually buy a kit of them relatively inexpensive. I think it's like $30 or something like that for a kit of I think 85 different values and 100 resistors of each one. So it's basically 8,500 resistors in a kit. And so what I wanted to use, they're all standard values following the standard resistor value settings. It came with this sheet which tells us all of the standard values. So it's the E12 series, 85 values, 8,500 pieces from Farnell, Element 14, Newark. And so these are the values that I have available to me for this project. So it lists every single value that's there. I will provide a link when I do the video and do the write-up to the part number for this, so that you can have a look at it yourself. So the reason why a lot of the values in my converter, in the differential amplifier are what they are, and therefore having slightly funny gains and things, is because I've made a point of only using values that are available in that set. Anyway, so let's get into this board and start having a look at how it works. So we'll start off with the voltage control circuitry. So right off the bat, I want to apologize for the flickering on the 3 of my meters are using OLED displays, and unfortunately under camera they tend to have this flickering effect. So I apologize for that. There's nothing much I can do about it. So what I've got is that these two are set up for measuring the current. So they're turned off right now because we're not looking at that stage initially. These two, the Keysight 1461 is looking at our V set point, which is going to go from 0 to plus 5 volts. The true RMS multimeter here, the Agilent 1272A, is going to be looking at the output of the differential amplifier. Right now it's actually, I think, plugged into the summing junction. So let me just move that to the output of the amp. So that's set on the junction of the summing amp. I'm actually not, currently there's no voltage turned on from my power supply. What I'm using is my Keithley triple output power supply. I'm using the 0 to 30 volts output to simulate the output of the main power rail for the sensing. What we'll do is before the end of this video and the very next video, I will hook up the power supply actual power stage into it from a transformer and everything else so we can see the actual output going. For right now, I want to demonstrate how the differential amplifiers and things are going to work and how the control circuit is going to work. So I'm not going to hook up the power stage at the moment. I'm just going to drive the output voltage from the Keithley power supply so I can just set it to what I want, which means it eliminates part of the control circuitry from what we're trying to learn here today. And when we do the current one a little bit later, I'm going to use the 0 to 5 volts 5 amp output of the Keithley power supply to drive a load through the current sense resistor, which is right here. This is one of the Vichy precision current sense resistors, 4 terminal. In case you're wondering why I've got these big ass crocodile clips on here, is in the previous video where we were looking at measuring current and everything else, I don't know if you've seen it or not, but I actually managed to fry. I've got these are about 10 or 15, maybe a bit more dollars. They're actually Agilent. They're 300 volt Cat 2 rated, and it says on them that they're rated up to 3 amps. And basically I melted them because we were putting in, I went up to about 4 amps on the current flowing through these things, and the probe metal just basically overheated and melted completely through the plastic and ruined the probe clips. So I had a long dialogue with Agilent about exactly what the rating of these things are, and even though this is Cat 3 rated up to 300 volts and 3 amps, if you go to the 3 amp rating is the absolute max. It's not a normal operation range. So be aware of that when you're using things like this, that, you know, just because it says it'll do 3 amps on the packet, if you go slightly above that 3 amp rating, you know, and even at 3 amps, these were starting to get warm. But if you go above that, you're going to wreck the probes. And if I had, you know, at the time I only had about 2 or 3 volts on these probes, so it was nothing dangerous. But if I had had 300 volts at 3 amps or slightly above going through these when they disconnected, that could have been disastrous. I mean, it could have let go and contacted with a person. It could have shorted something out and blown up some equipment or something like that. So just be aware of the fact that when you're connecting probes, make sure you use the right ones. This was my own fault because I was actually exceeding the current rating of these anyway. But nevertheless, you know, when I was looking at the rating, I figured that, oh, they're rated for 3 amps. So if I'm putting over a little bit over 3 amps, yeah, they might get a little bit warm, but they should be fine. Just the readings might be slightly off because of cable resistance and stuff like that. But no, it's more than that in this case. They actually will melt, and you will get some serious problems if you're dealing with any dangerous voltages. So just be aware of that, and hence, you know, the clips that I have on here, these are actually rated at 10 amps, so shouldn't be an issue. The trouble is they're just huge on my breadboard, so I've tried to keep them out of the way, but nevertheless, you know, it means that I'm not going to be melting and damaging more probes when we get to that bit. Anyway, back to the testing here. So I just wanted to mention, in case you were wondering why these big ass things are here. So here's our op amp. We're running on plus 12 and minus 12 supply. So the box that this is all in, this breadboard box, there's actually a power supply inside it that's giving these. I've had this board since I was about 17 years old. So what, nearly 40 years I've had this thing, and it's still going strong. I used it when I was learning my electronics way back, and you know, I built it up for stuff like this way back then, and I, you know, only started using it again a few years ago. So it's seen a lot of work over the years. But anyway, the op amp's plugged in here. I've got the plus and minus 12 volts coming in. I've also got plus 5 volts. Now, the plus 5 volts here is just a nominal 5 volts, so it's not a VREF. So I'm actually using this to feed my 2 adjustment potentiometers for the sake of this experiment. So these two pots, they're just being fed from the 5 volt here, not of a 5 volt reference. So that's why I'm measuring the output on this meter so that we can actually see what I've set, rather than trusting that when the pot's cranked all the way over, it's going to be 5 volts. We can actually measure it. The output from here is, as I said, it's measuring the difference of the input. And because of where I've connected it, I've hooked it up right now to get that in a little bit. So this is where we've got the power supply. When I turn it on, that's going to be the 0 to 30 volt in to this difference amplifier. And right now my probe is connected to here, so that I'm measuring the 0 to 6.6 minus 6.6 volts on this point as I vary the output of the power supply. And my set point that my other meter is reading is actually reading this. I've got just a impedance converter op-amp configuration with the pot wiper feeding into the plus of the op-amp so that we get a low impedance source coming into here. We'll look at this value in a minute, but for now we're going to look at this part of the circuitry and look at what's happening on here. Sorry about the beeping, it's just my meters turning off because I'm ignoring them for too long. So let me output, I'm going to set the voltage for, let's just go right to 30 volts first of all, so we can see if we get the correct output. So I've set 30 volts on the output of the power supply, and I've just turned it on just to show you that. The Keithley power supply right here. All right, that's my 30 volts, well 29.999, it's close enough. Just connected, so there's the two connections coming out of the power supply. One's for current on the right hand side, the other one on the left I'm using for the voltage supply, pretending that's the output of the power supply, which I guess technically it is the output of a power supply. We're just not controlling it with this circuit at the moment. So here's our 2 meters, and you can see right now that there's no point in showing you the circuit because that's all buried in amongst that big pile of wires there. It's not much that you can see. As I say, they're all 5% resistors, and it's exactly the ones that I've shown you in the schematic. So let's just put it up on the meters, and we'll just see what the meter is going to show us. This is now reading minus 6.548, so 6.55 volts. It's supposed to be reading minus 6.6, but as I said, these resistors, I haven't physically measured them yet, but they're all 5%. So you can expect that you will have a little bit of difference here. But for the purposes of what we're doing, this is more than close enough. And as I said, you know, if you're working this in an analog system, you would have a panel meter on the output of the power supply to tell you what volts you're actually outputting, or you'd have something on the current to measure the current and showing you on a meter as well. So you would actually have an accurate reading of the real current going out and the real voltage going out. If you wanted to be able to have a set point value shown where you don't actually have the output on while you're setting your voltage limits and your current limits, then you might want to play around with the values. But I mean, you could feed this set point, right now it's 4.9. All right, you would adjust the gain slightly, but you can either put a potentiometer, like a little trimmer pot, across the one of the feedback resistors to trim its value. If you're using a DAC from a computer, you just simply offset the output voltages and things from the DAC in software to compensate for the fact that it's not exactly what you want. And that's how all modern power supplies and DMMs and everything else, they don't have high tolerance parts in them anymore. They just have high stability parts, and they have they don't drift over time, but they're not accurate. And all of the accuracy, you've got a stable voltage reference that you can rely on, and everything else you're just using software calibrated control, where you're just compensating for everything in software, and it's easy to do, relatively speaking. I mean, obviously it takes coding and things like that, but it eliminates a lot of the hassle that you used to have in old school electronics. Now, I say old school, but some of the inspiration I've got for the circuits that we're looking at, I've actually derived from looking at some 30-year-old power supplies from Agilent, Keithley, and other manufacturers, to draw some inspiration of how to do some of this stuff, just to brush off the cobwebs. And these are ones that I was using when I was back in my electronics apprenticeship days, way back. So anyway, what we've got here right now is we're seeing that our gain is basically, it's off just very, very slightly, but 6.5 5 versus 6.66, it's within a percent or so of what we want, and so that's going to be just fine for our control circuitry. And so now let's have a look at what the difference output is. So I'm going to move the connection now on this board from right now I'm sitting here, which is going back to the schematic. I'm connected right here at the moment, so I'm going to move the connection over to here, which is now, the difference of this summing value, the VSET value and the difference value coming in here. This, with this set to 5 volts and this set to 30 volts, this should be roughly 0 volts. Now, obviously, these are, as I said, 5% resistor values, so they're not going to be perfect here, but you can, as I said, you can compensate for that in software. So let's go see what we've got. All right, moving this now, that's my output from there. I've got 2 resistors. Helps if I take the right one. And so we've got our 120K and we've got our 12K. So right here is where we want to hook on. And then this resistor here, which is just buried underneath all these wires, this one here is the 100K coming from VSET. So this meter now, let's go back up to the meters, is this one here is now reading the junction voltage of that summing amplifier. So remember in the circuit here, it's reading here now. So we've got the 6.6 volts. We know that goes up to 6.55-ish here. There's our junction, and there's our 5 volt VSET coming in, right? So this should be about 0 volts. And what we have, as you can see right here, is we have basically 50 millivolts. So that is actually pretty good. If I adjust the VSET point a little bit, I can probably just take that down. All right, I'm bringing down the VSET just to see how close I can get that to 0. Oops, it's gone the other way now. And the difference of 0 will become relevant when you see how we're going to control the circuitry. All right, so it's taken that down to there. So I've actually am inputting a VSET point of 4.9 volts into the VSET, and I have 29.999 volts going into the differential amplifier. So you can see if you were using a DAC to drive that, or if you just simply had a, I'm using these pots. If you put a simple little trimmer resistor in series with the pot, you can very easily trim the high end of that so that you only have 4.9 volts as the maximum, and that now would automatically give you the correct output on the difference junction. So if I bring down the voltage of the power supply to say 10 volts, which indicates, we've got a set point here of 5 volts, meaning we want to have 30 volts out. But if I say if I just bring it down to 10 volts for a moment, you'll see that immediately summing output has now gone to plus 1.85 volts, indicating that we're way too low on our output, and we need to be able to compensate for that in the control circuitry. And if you remember our conversation just a few minutes ago, it might be about half an hour ago now, about the way that we're going to drive these MOSFETs, all right? Here, remember this. What we said was the V control, if it goes down, it actually turns the output off. If it goes up, it allows the output to turn on. It doesn't drive it on, it just allows it to turn on, providing none of the other control inputs are limiting it. So what we've got here right now is that we've got plus 1.8 volts, which represents the difference between a 5 volt set point representing I want 30 volts and the fact that we've only got 10 volts being sensed. Our output now is plus 1.85 volts. So what would happen on here is that this, because it's now positive, would be allowing this to be driving upwards if I was connecting directly to here. All right, it would allow this to drive up. Now 1.85 volts on here would not be enough to be able to turn this on. So we're going to have additional circuitry in here, which we're going to look at later. But basically, by going positive, it allows the output to not be turned off. If you think about it, it's working in reverse. The amplifiers will turn the power stage off, they can't turn it on. They can only allow it to be turned on because of this pull-up circuitry. All right, so that is showing us there. Let me just now adjust the VSET point. So that's representing 10 volts in, giving us that. So if 5 volts represents 30, then divide that by 3, so 2.5, 2, 4, 6, so about 1.8 volts or so on our VSET point probably will 5, 2.5, 2, yeah, about 1.8 to 2 volts without doing the math. On the set point on this meter, this should basically come back to about 0 based on all things being equal. So as I crank down my set point, you can see now that the voltage here on the output of the summing junction is now creeping down towards 0. So it's half a volt, 0.3 volts, 0.2, 0.1, and there we basically have it. So I said about 1.8, I wasn't far off, 1.7. All right, and at this point here, basically the output now would be, assuming that the output is now equal to the set point that you want, because the output of that summing junction is now correct. Now, those of you that have looked at the earlier circuits are going to be saying, well, if you've got 0 out, how are you driving the Mosfet? Because that's not going to be doing anything, and that's what we're going to look at a little bit later for that stage of it. But for now, this is about how do you detect the differences, and this particular output now is showing us that there is no difference between our set point and the voltage that we're actually detecting from the output of the power supply. So if I actually take this even further down, so say I set this to 1, which would represent 20% of the output, so you know you can see now that the output has gone negative, meaning that it would be trying to turn on the drive harder the Mosfet so that it outputs more voltage to your terminals, and once the voltage it will be trying to turn the Mosfet off such that because it's got too much volts on the terminals and it needs to pull it down. So remember, we're working in reverse with the Mosfet. So as we pull it down, if I actually go to my power supply and start cranking this down, you'll see we're at 9 volts, 8 volts, 7 volts. So around 7 volts, you see we're back down to the, that's too far. So around 6 volts now, representing this 1 volt here. We're now back into roughly equilibrium. So that's showing us now that this difference, the differential amplifier and the summing junction is working exactly as we want it to do. So let's have a quick look at the current side of this and see if it works in a similar way. All right, so for the current, what I'm using is this 50 milliohm Vishay precision current sense resistor. It's got a little heatsink on so that it can take up to, I think, about 10 amps. I'll have to verify with the spec sheets. I've used this on previous videos for current sensing. And what I've got is on the outer 2 terminals, I've got my output of my Keithley 2230G power supply. I'm using the 0 to 6 volt range because it can output over 5 amps on that one into here, and we want to have up to 5 amps. And the inner 2 terminals I'm actually sending to the input of the current controlled amplifier, which is got the one that has the positive gain rather than a negative gain, and that's basically this one. Let me just zoom that out a little bit there. So that's our 50 milliohm resistor right here. That's this here, and we've got a 210Ks feeding into the op amp, and then we're going to connect our meter to this output, which is basically pin 1 of the op amp. All right, and we've got our set point that's going to be 0 to 5. So the first thing we're going to do is verify that our current sensing is working, where we go 0 to 5 amps, and we should get 0 to about 4.75 volts on our output of the difference op amp. Okay, so let's have a look at the meters and see what they're telling us. So right now my current set point is set to 0 volts, which is fine because we're kind of ignoring that right now. And my power supply I've set to 0 amps. So obviously it's in constant current because, well, 0, you've got no choice. And I'm reading a slight offset of about 19 millivolts on here. And as I said, that's okay. You can, as I said, you can compensate for things like that in software, but it's also on the positive side of things which means it's not going to be driving the output any harder on anyway. So let me just start now. Let's just go straight to 5 amps to start with, and what we should get based on our circuit design is around about minus 4.75 volts on the difference on this one here. So I'm just going to go straight for gold and go 5 amps, and we'll see what we get. So as I said, it should be 4.75, and we're getting 4.69. So again, that's well within the ballpark of what we were expecting. Again, 5% tolerance resistors. If you did 1% or 0.1% resistors, obviously things are going to be a lot more accurate for what we need, but I was using standard off-the-shelf parts. As I said, you can trim them, or if this is good enough, because of, you know, if you're going to be computer controlling this, or with simple adjustments of the VREFs and stuff, then it really doesn't matter as long as they're balanced and stable. I'm not sure whether these ones are terribly stable. They're just the ones for the sake of the experiment that we're using. So that's good. We got minus 4.7 volts instead of more 4.75. So again, it's within a 1 or 2% of our control limits. Now let's just move the probe to the output of the junction of the summing resistors. So that will be the very next one. So what I've done now is I've moved the instead of measuring here, which is where we were a minute ago, ignore these pin numbers. I've actually wired the op amp. I've marked the diagram with the wrong numbers. So instead of being connected here, we're now connected to the junction of our set point resistor and the output of the op amp. So right here. So because I have 0 volts set on my potentiometer, so I've got 0 volts up here, then I've got, you know, maximum current flowing through the meter of 5 amps, then this here should be reading quite heavily negative. Yeah, I got 5 amps in, and I'm asking for 0, so I need to basically drive the MOSFET hard off. So this difference output being minus 2.3 is attempting to drive the MOSFET off. Again, ignore what the actual value is. It's the fact that it's gone negative is what's going to be relevant when you see the next part of the circuitry. So my fans are just starting to come on my power supply because I'm pulling 5 amps out of it, to just ignore the humming in the background. So let's now see what will happen here as we vary this set point up to the 5 amp setting, which is basically, you know, according to our calculations, 4.97 volts. So remember, the right hand meter here is telling us our set point. So I'm now going to vary the current and increase this towards, well, I'm going to take it straight to 5 volts to start with. The fan increasing in speed is nothing to do with me changing this set point, by the way. So I said it should be 4.97 roughly, but remember the tolerance of the resistors and everything else. So 4.9 still is what the voltage is that I'm setting on that particular one. And again, nothing that a trimmer couldn't adjust. So I've got 5 amps going in. I can trust the fact that I've got 250 millivolts on my precision current shunt. And I've now got a difference output of 0, well, to all intents and purposes 0, from that. So if I now reduce the current to say 1 amp, we should see this go high because it wants to allow the power supply to turn on harder to try and get that current. So if I just drop it straight to 1 amp, see, now it's going high here. So now I need to drop the volts on the set point here to about, about 1 volt basically, because we've got 0 to 5 and 0 to 5. So it will be about 1 volt. So let's just start cranking this down and see if roughly 1 volt we start getting equilibrium again. So 0.95, 0.96 volts, yeah, 0.97 volts roughly. We're now back in equilibrium again. So as you can see, the current control circuitry here is working just as we predicted it would from the design and from the outputs. That's working just great. As I say, inspiration from Agilent and other power supplies that I've looked at over the last few months. And we know now that our voltage control, which we were looking at before, is working perfectly fine within allowable tolerances for the sake of the test. So the next step now is to look at how are we going to control the MOSFETs? Because we already know from previous videos that, actually let me just turn the power supply off so it stops the noise. Sorry about that. So the next step of what we want to do here, we already know from previous videos and experimentation that when we drive a MOSFET, especially an N-channel power MOSFET, and by the way, you can apply this same control logic to a P-channel MOSFET, or you can apply this same control logic to just a regular BJT, NPN power transistor if you wanted to. You just have to tweak this control circuitry a little bit. What we've got over here on the control side of things is going to be the same no matter what you do. You just may have to invert your sensing to give positive control versus negative control and things like that. But what we want to do is be able to pull these down in order to turn this off. So left to its own devices with this configuration, this power MOSFET is going to turn on, and it's going to turn hard on. So the output will be maximum, your current will be maximum, etc. And all these control circuitries are going to be there to keep it controlled and turned off. So that's why the outputs go negative when we want to turn things off, and they go positive when our measured set point is above our, where our measured value is above our set point. So we want to be able to have that a piece of circuitry between our set points and our outputs of the different amplifiers and these control points in order to control this in a stable manner. Now, one of the things that a few people have been asking me is noise immunity and things like that as well, and also transient response times. Well, I don't know what transient response times we're going to get right away with this, because I haven't finished building all of the circuitry and testing it. But I do know that we want it to be able to track various loads without breaking into oscillation. You probably want to, if you switch the output from, say, 0 amps to 2 amps or something like that from a load perspective, you do want to be able to make sure that the power supply output voltage doesn't go drooping way down, by a volt or two, and then come back up again over the period of a few seconds. You want it to be able to recover within, probably less than a millisecond if you can. To things like that. Now, obviously, having capacitors on the output stage, small value, maybe 10 microfarads or something, will help for a little bits of spikes and things. But you want to have some control mechanism that will actually allow you to take those differences of your current sensing and or voltage sensing and translate them into something that will control the output, but then continually adjust to bring it back into the desired value of output. So what I'm going to put in on mine is I'm actually going to use some integrators. Again, these are just very straightforward circuit with an op amp, and it just takes the output of the differential amplifiers and it will convert it into a continually positive or continually going negative output up to the limit of the supply rails of the op amp, and you can use this to drive whatever circuitry you need. So we already know that the FET is going to go high automatically if you're not driving negative through the diodes, because the diodes are going to prevent your control systems from pushing the output, the input of the MOSFET high. So these control circuitries are going to be pulling low when you want to turn the outputs off of the MOSFET. So that was fun. We've just finished now looking at how to differentially measure the output voltage of our power supply, and also how to measure the current using a current shunt and differential, well, not quite differential, but almost differential amplifier, and how to use the summing junctions so that we can feed it into another stage of control for our power supply. And we've also looked at how I propose to deal with controlling the power MOSFET on the output stage by using a 15 volt or 12 to 15 volt supply, using a bit of a Zener and a dropper, and having the control circuitries only allowed to pull down the MOSFET to turn it off. This allows us to parallel up a number of control circuits if you want to, and have different things like a delayed power on reset and things like that to make sure that we don't get spikes on the output and everything else. So in the next video, I'm going to break it right here because these things are getting quite long, and I'm going to immediately now go into another video which will follow on from this to deal with driving the output using an integrator. So what that's going to do is there's going to be an integrator for the current and an integrator for the volts, and we're going to use those to control the output of the power supply. And the idea is that, as you saw with the summing, as long as the output was equal to the set point, then the output of the summing junction was 0 volts. Now if you've got an integrator connected to that, the minute it goes off away from 0, then the integrator is going to start to ramp in one direction or the other depending on which way from 0 you've gone. And we're going to leverage this to set a certain amount of control on our response times, and also allow us to change the output response time based on how much of a deviation there is. And I know that's normally like in PID controllers, that's the derivative, but what you do with the integrator is, depending on the size of the offset on the input, you can get a relatively faster change on the output of that integrator. So we're going to have a look at that. Anyway, I'm going to finish this one here because we've looked at the differential current measuring, we've looked at the differential voltage measuring, we've looked at the summing of each, and we've actually had a test of both of those, and we know that they work just fine as expected within the tolerances of the components we're using. So let's go and now look at the integrator as a separate video and go from there.